Hello everyone, and welcome to OneClass. My name is Jeff Krause. I have a PhD in physical chemistry, and today I'm going to go through a few undergraduate, high school level physics questions. So here we have our first one. Four long parallel wires each carry 2 amps in the same direction. They are parallel to the z-axis, and they pass through the corners of a square of side 4 centimeters positioned in the XY plane. What magnetic field does one of the wires experience due to the other wires? So we have 1, 2, 3, 4. So this is our square. Of side length 4 centimeters. And so it says they're parallel to the z-axis, so this here is our XY plane. And from the right-hand rule, the z-axis will be out of the page. All right. So if we're trying to figure out the B field at 1 due to the other 3 wires, we can use our expression for the B field due to an infinite wire, but remember that B is a vector. So this gives us our magnitude, but we also need our direction. And our direction comes from our right-hand rule. So the B field due to, if we look now, we're going to focus just on the 1 wire and get the B field due to 2, 3, and 4 on 1. So if we're looking, and right now I'm just going to do B to 1. So my magnitude is mu naught I over 2 pi r. My r is 4 centimeters. My I is given in the question as 2 amps. So my B21 is 4 pi times 10 to the minus 7 times by 2 amps over 2 pi times 0.04 meters, as 4 centimeters is 0.04 meters. Okay, if we do that out on our calculator, we get 1 times 10 to the minus 5 Tesla. But now we need direction. So remember that we use the right-hand rule here. So we've got 2, 1, there's our R. And we're talking about from 2 to 1, so we would put our thumb in the direction of the current, and then our fingers would curl in the direction of the B field. Okay, so now picturing our thumb going out of the page, we see that the B field would curl this way, so this is the direction. And in fact, at R, it's going to be straight down. So looking at our X, Y, our B21 is then minus 1 times 10 to the minus 5 Tesla in the y hat direction. So that gives us our full directionality there. Okay, now we can do 4 pretty readily as well, right? So 4 is going to be pretty much the same as 2. So B41 magnitude is mu naught I over 2 pi r, which is 4 pi times 10 to the minus 7. I should have put some units on there, but that's going to be just Teslas, meters per amp, times 2 amps over 2 pi times our 0.04 meters, which is again 1 times 10 to the minus 5 Tesla. But now our 4, 1, applying right-hand rule again, with our thumb pointing out of the page, then we get that the B field will be in our negative x direction now. So B41 vector is minus 1 times 10 to the minus 5 Tesla in the x hat direction. Okay. And then, so 3 is now the trickier one. Okay, and now we've got a size of 4 centimeters. So, so our r here is square root of 4 squared plus 4 squared, which comes out to 5.657 centimeters, or 0.05657 meters. And so we can easily solve for our magnitude as mu naught I over 2 pi r, 4 pi times 10 to the minus 7 Teslas meters per amp onto 2 amps over 2 pi times 0.05657 meters, which comes out to be 7.071 times 10 to the minus 6 Tesla. Now our direction is going to be a bit trickier. So we can see that here's 3, here's 1. Again, using right-hand rule, it's going to be perpendicular to the r and pointed downwards in this direction. So our r vector we can figure out, and this is going to be our B41 hat. Our unit vector in our B41 direction is going to be that way. And so we know that, B31, our B31 hat is going to be, so the right-hand rule really expresses that it's going to be K hat cross R hat. R31 hat. And, right, so if we figure out what R31 hat is, which is R31 vector over R31 magnitude, which is 4 centimeters in the minus 4 centimeters in the x hat plus 4 centimeters in the y hat. We're calling our axis system. Over our magnitude, which was 5.657 centimeters. This comes out to be minus 0.70709 x hat plus 0.70709 y hat. And we can, so we can easily get our B31 hat now as k hat cross with this expression. And the way I remember how the unit vectors all cross product is pretty easy. So x hat cross y hat is k hat. And then it rolls through. So y hat cross k hat is x hat. And k hat cross x hat is y hat. And then if we want to switch them, it becomes negative. So y hat cross x hat is minus k hat. K hat cross y hat is minus x hat. And x hat cross k hat is minus y hat. So if we look here, this is going to be minus 0.70709 k hat cross x hat plus 0.70709 k hat cross y hat. And so we can find these in here. So k hat cross x hat is y hat, and k hat cross y hat is minus x hat. So this is minus 0.70709 y hat, and then minus 0.70709 x hat. So our B31 vector is our B31 magnitude times our B31 unit vector. So we get 7.071 times 10 to the minus 6 Tesla times minus 0.70709 x hat minus 0.70709 y hat, which comes out to be 5.00 times 10 to the minus 6 Tesla times minus x hat minus y hat. All right, so now our B field at 1 is just equal to the sum of these. Which is minus 1 times 10 to the minus 5 Tesla y hat minus 1 minus 5 times 10 to the minus 6 Tesla x hat plus y hat. So I just took the negative out of there. And minus 1 times 10 to the minus 5 Tesla x hat. So this comes to be minus 1.5 times 10 to the minus 5 Tesla x hat minus 1.5 times 10 to the minus 5 Tesla y hat. And then if we want to know the magnitude of our B field at 1, well, that's just the square root of the component squared. And I've gotten rid of the negative sign as negative. The square of a negative is a positive. And that comes out to be 2.1 times 10 to the minus 5 Tesla. And so then there's our B field at that one due to the other wires. And because of the symmetry, the magnitude would be the same, although the directionality would be a little different. So for all the other wires. So then there's our total B field. And all right, so checking to the solution given. So they just added it all up and get 2.7. So the discrepancy here is because they didn't treat them as vector quantities properly. So magnetic field is a vector and needs to be treated as such. All right. And there's that. So here we have a rider goes down a water slide, and it gives in the figure that we have a 45-degree slope. So some rider at the top with our mg as such. We're going to set up our axis system as x, y. And it just wants to know at the end of the first section, so the 6-meter slide, what velocity are they traveling with? So we can write our draw our free body diagram as mg, and decompose it into our xy axes. So our triangle that we've drawn here, that's our 45-degree angle. There's our mg. So our mg cos theta is here, and our mg sine theta is here. So looking in the x direction, our f net x is just purely mg sine theta, which is equal to our ma. So our masses can cancel. Our acceleration is then just g sine of 45 degrees, which is 6.930 meter per second squared. So that's our acceleration. So now we can readily solve for our speed at the end of the travel. So our xf is equal to our xi plus vit plus 1/2 at squared. So this is 0. We're starting with no velocity, and we're calling our initial position 0. And our xf is our 6 meters. 6.930 meters per second squared, t squared. So we can say that t is root 2 times 6 meters over 6.930 meters per second squared. Okay, so then we're just interested in velocity, so I'm just going to leave that like that. And our velocity is our initial velocity plus our acceleration times our time. That's 0. So our velocity final is 6.930 meters per second squared times our time, which is 2 And so this is square root of 2 times 6 meters times 6.930 meters per second squared. So if we do that on our calculator, we get a VF of 9.1 meters per second. Checking through our solution here, we get indeed 9.1 meters per second. So that looks good. Another fairly simple one. So we've got a car travels east, and I'm going to call east my x direction, and west my negative x direction, and north will be my y. But that doesn't matter here. So my first displacement is 2,000 meters in the x hat direction. My time is 10 seconds. It then travels west for 500 meters. So minus 500 meters in the x hat, and my time is 5 seconds. So then my total displacement is 2,000 meters minus 500 meters, which is 1,500 meters in the x hat. So then my average velocity is my total velocity, I guess, is my total displacement over my total time, which is 15 seconds. So 1,500 meters over 15 seconds, which is 100 meters per second. My average speed, though, is my average distance. So my total distance, which is just the sum of my distances without direction. And so my average speed is just my total distance over my total time. Which is 150 meters per second. So just to emphasize the difference here, right? So a velocity takes into account direction. So it's the displacement over the time, and the average speed is just the total distance over time. Checking through the solution here. 2,500 over 15, is that? Oh, maybe it's not 150, maybe. Maybe I punched that in funny. Because that actually does kind of not make any sense. Yeah, sorry. So that should be 166.67. I must have just done a small mistake there. So that looks good. Okay, so here we've got an application of Gauss's law. So Gauss's law is just that E, for a simple volume anyway, EA is Q enclosed over E naught, where area is the area of the volume that's enclosing the charge. Okay, so we've got a uniform sphere of radius 5.0 centimeters, and wants to know the magnitude of the electric field at an R of 3.5 centimeters for A. So that's inside the sphere. So our Q enclosed will be the charge density times the volume enclosed, which will be 3.2 times 10 to the minus 3 coulombs per meters cubed. The volume enclosed will be 4/3 pi times our 3.5 centimeters, or just R cubed. So R being less than R. And our area in all cases will be just 4 pi R squared. So we can say that E times 4 pi R squared is equal to 3.2 times 10 to the minus 3 coulombs per meters cubed, 4/3 pi R cubed over E naught. We can divide out the pi and the 4 and get our E field is 3.2 times 10 to the minus 3 coulombs per meters cubed over 3 E naught. And we can get rid of R squared, and this drops down to just R. So then we can plug in our R value, which is 0.035 meters over 3 times our E naught, which is 8.8542 times 10 to the minus 12 coulomb squared per Newton meters squared. And we can see that one of the coulombs will cancel, and our meters squared will cancel completely, and we'll end up with newtons per coulomb, which is our E field unit. And so this comes out to be 4.22 times 10 to the 6 newtons per coulomb. Okay, and then for B, it's outside the sphere. So then EA is equal to Q enclosed over E naught. Q enclosed in this case is the entire sphere. So it'd be the rho, or the density, times 4/3 pi the radius of the sphere cubed. As it encloses the entire thing, but the area that we've got now is still the same area, so 4 pi R squared, where R in this case is our 8 centimeters. So our E field is going to be 3.2 times 10 to the minus 3 coulomb per meter cubed, 4/3 pi are 8 centimeters, or 0.08 meters cubed, over E naught times 4 pi. Our R is 0. Oh, sorry. The big R should be 0.05 meters, because that's the radius of our sphere. And the little r will be 0.08 meters, because that's the radius of our volume, or our surface area of our volume that we're enclosing. Okay, so 4 and pi will cancel again. the r's will no longer cancel. And if we do this out on our calculator with E naught as above, so the same constant as we used before, this becomes 2.35 times 10 to the 6 newtons per coulomb. Okay. All right, and so we can check through the solution here. And so inside the sphere it's 4.22 times 10 to the 6, and outside it's 2.35, 2.36. So that would be just rounding differences. And I think a different E naught that they used as well. Okay, so the solution is correct. Okay. So now we've got a person standing on an elevator. So, not a scale, in an elevator I should say. So their mass is 98.1 kilograms. So before it moves, the only force is mg and a normal force. So the normal force is from the scale. So F net is equal to normal minus mg, which equals 0, as the acceleration is 0, so we're not moving yet. So then n equals mg. So the scale reads n over g, which equals m. So that's what the scale reads, is its normal force over g, or the force it needs to apply. So when now the elevator is accelerating upward, then we've still got an mg, we still got our normal, and we've got an acceleration of 1.47 meters per second squared upward. So n minus mg is equal to ma. So n is equal to ma plus mg, which is equal to our mass, 98.1 meters per, no wait, yeah, 98.1 is right, but it should be kilograms. Our acceleration is 1.47 meters per second squared, and our g is 9.8 meters per second squared. And so this comes out to be 1105.587 newtons. And so the scale will read so it still will read n over g. So 1105.587 newtons over 9.8 meters per second squared, which is 112.815 kilograms. And so just as a check here, right? So when an elevator is accelerating upward, that's either at the beginning of an elevator journey upwards or when it's coming to a stop as it's traveling down. And so you'd always feel heavier when that happens. And so a scale would read heavier. So that makes sense. If we check the solution here, so they calculated a net acceleration and got an apparent weight that was actually less, but that doesn't make sense from what we were just saying, and so that's just incorrect. And the best way to do it is just to break the components down as opposed to trying to find a net acceleration. I don't actually know how to look at force components and how scale reads mass. So I'm just going to do that. All right, so here we have a 100-gram particle, which experiences the force that's pictured in the figure. I'm just going to re-sketch it a bit. So here's our x, minus 10, minus 20, and it keeps going up until about 3 meters. So here's our 1 and our 2, at which point it, a rather straight line, goes to 4, and then continues 0. Okay. So if we start at 1 meter with a speed of 21 meters per second, it asks at what x is the turning point. So remember, a turning point is where our VF equals 0. We're giving a force as a function of distance plot. And so what that always makes me think of is our potential energy. So our du is minus F dx, or our potential energy can be found from our area. Since it's constant, at least in here, so as long as we don't go past 3 meters, then we can say that this is just minus F delta x. Our delta, we can say that, we can say that delta U is minus F delta x. So we know that delta KE is minus delta U for a conservative force. So we were given it was a conservative force. So then it equals F delta x. Okay, so then we have at 1/2 mVF squared minus 1/2 mVI squared, which is delta KE, is equal to F delta x. That's 0 for our turning point. So then minus 1/2 mVI squared is equal to F delta x, or delta x is minus 1/2 mVI squared over F. So again, as long as we don't surpass 3 meters, our F is minus 20 newtons from the plot. So our delta x is 1/2 100 grams, so that's 0.100 kilograms, times our initial velocity, which is 21 meters per second, and over our minus 20 newtons. So minus over a minus is a plus. So then doing this out on our calculator, we get 1.1025 meters. And so that's our delta x. So xf minus xi, which is xf minus 1.0 meter, because that's our starting point, is equal to this 1.0125. And so our xf is 2.1025 meters. And we can check it doesn't surpass the 3 meters, so all of our assumptions for our force are validated. If it had, we'd have to go back and do some extra stuff, but we don't need to. So that's our turning point. 2.10 is our turning point, so that looks good. All right. So we've got a plot for an RC circuit here, and so it's obviously discharging. In an RC circuit, our voltage as a function of time is our initial voltage times e to the minus t over tau, where tau is our C. So the resistance times the capacitance. We're given that it was fit to a V equals 5 e to the minus 2t. So we can see here that V naught is 5, and 2 is equal to 1 over tau. So 1 over RC equals 2. And we're given now that the resistor is 1 times 10 to the 6 ohms. And that's to compute the capacitance. So the capacitance is 1 over 2R, which is 1 over 2, times 1 times 10 to the 6 ohms, which comes out to be 5 times 10 to the minus 7 farads. So now if we check the solution here, we just compare it to this function and get 5 times 10 to the minus 7, or 0.5 microfarads. So that looks good. Okay, we've got fresh water behind a reservoir dam. So we've got a dam of depth D. And then we've got a pipe of radius R located at a depth D. Passes through the dam and we've got a plug firmly inserted in the pipe. Standard gravity acts vertically downward, and standard atmospheric pressure is present. Okay, so if we look at the pipe, or the pipe inside the dam here, the pressure at D is going to be atmospheric pressure plus rho GH, which is 101.325 times 10 to the 3 pascals, plus our density of water, which we're using as 1,000 kilograms per meters cubed, times our gravity, 9.8 meters per second squared, times our depth, which is given in the question as 6 meters. So that's our pressure. Now, okay, so that's our pressure at that depth from this side of the dam, but there's also a pressure from this side of the dam, which is actually just going to be atmospheric pressure. So now if we look at, to get the frictional force on our plug in our pipe, we can draw a free body diagram. So we've got a force due to the water, we've got a frictional force, and we've got atmospheric pressure. So then F net is equal to the force due to the water minus our frictional force minus our atmospheric pressure, which is equal to 0 as it's not moving. Our force due to the water, so recall that force is pressure over area. Recall that pressure is force over area. So then force is pressure times area. So our F water is 160.125 pascals times our area, which is pi r squared. And our atmospheric pressure is 101.325 pascals times our area, pi r squared. So then our frictional force is Fw minus F atmosphere, which is 160.125 minus 101.325 times our pi r squared. Our r in the question is given as 2 centimeters, so 0.02 meters squared. And so our frictional force comes out to be 73.89 newtons. Okay, and now for B, it asks the total volume of water that exits the pipe during a 3-hour time interval if the plug is removed. So for this, I consider just the pipe. And now at this side of the pipe, we're going to call the kinetic energy 0. And the potential energy, just rho GH. And over here, we're going to call the potential energy 0. And the kinetic energy and then we need the kinetic energy on this side. So if we consider what did I do there? So delta U is equal to minus F delta X. Our force without our friction is just, if we look above, is just our force of our water minus our atmospheric pressure. So it's purely the it's purely just this expression. Oh, right, it's just the friction essentially, but the negative of it. So it should just be 73.89 newtons. Oh wait. Alright, I shouldn't go off script too much here. So it's just F delta X and our force is just our pressure times our area, dx. Oh, right now I see. Okay. So our delta U is minus our pressure times our area times our dx. Our delta KE is equal to our pressure times our area times our dx then. And so our delta KE is going to be 1/2 mv squared, which is our pressure times our area times our delta x. So then if we call our mass our density times our volume, which is our density times our area times our delta x, then we can see that 1/2 mv squared is just equal to 1/2 density area delta x, and that's equal to pressure area delta x v squared. So then our v squared, we can cancel our area and our delta x. So you can see that v squared is just 2 times our pressure over our density. And our pressure is just rho GH. So it's 2 times rho GH over rho, which is just 2GH. So velocity squared for our water is just 2GH. There we go. So our kinetic energy at the output is then just 1/2 m times 2GH. So the 2's cancel, so our kinetic energy at the output is just mgh. Okay. I don't know if that's super necessary actually, but anyway. So we can solve for a velocity that everything's traveling at as square root of 2gh, which is equal to the square root of 2 times 9.8 meters per second squared. Our height is, or h is the depth, so 6.0 meters, which is 10.84 meters per second squared. So our change in volume we used as our area times our dx. So our change in volume with time is our area times dx by dt. So our velocity is our dx by dt. So this is pi times 0.02 meters squared times our velocity, which is 10.84 meters per second. And so then this is 0.0136 meters cubed per second times 3 hours. So you need to know, so I'll leave that actually. So now if we want to know how long it is for 3 hours, then we take our dv by dt and multiply it by our delta time. So 0.0136 meters cubed per second times 3 hours times 3,600 seconds per hour. And so that comes to 147.2 meters cubed. So our volume our total volume is 147.2 meters. 147.2 meters cubed over 3 hours. Okay. All right. So checking to the solution here. So we get our frictional force is 73.9 newtons, so that looks good. We can set v squared to 2gh and solve for our total volume as 147.2. What? Okay, 147 is what they gave at the bottom, and 143, so that must be just a mistake. So that looks good. Okay, so we've got two capacitors, one of 6 microfarads, and one that's 18. That are first completely discharged, and then connected in series. So the series combination is connected across a 12-volt battery. So we've got 6 microfarads, 18 microfarads. Okay. Next, they're carefully disconnected, so they're not discharged, and then reconnected to each other in parallel. So we've got, so it goes to here. And it wants us to find the potential difference after they are reconnected and find the energy stored before and after reconnection. Okay, so first off, we need to find the charge carried by these capacitors, and to do this, we need the equivalent capacitance. So 1 over C12 is 1 over C1 plus 1 over C2. So 1 over 6 microfarads plus 1 over 18. So our C12 comes out to be 4.5. Now our capacitance is the charge carried over the voltage. So our charge is capacitance times voltage, so 4.5 times 10 to the minus 6 farads times our voltage, which is 12 volts. So our charge comes out to be 5.4 times 10 to the minus 5 coulombs. And so this will be the charge carried by each device as they're in series. So 5.4 will be transferred here, and then will be transferred there. Now they're disconnected. Again, each will carry 5.4 times 10 to the minus 5 coulombs. So our total charge is 5.4 times 10 to the minus 5 coulombs plus 5.4 times 10 to the minus 5, which is 10.8 times 10 to the minus 5 coulombs. Now when they're reconnected, they will distribute their charges, but our Q total will still be 10.8 times 10 to the minus 5 coulombs, but that will equal our new charges on each capacitor. They will redistribute to maintain the same voltage, so V1 will equal V2, and we'll still have that our capacitance is equal to our charge over our voltage. So then, or rearranging this, our volt V1 is Q over C1. And I'll write it as Q1 prime. And V2 is Q2 prime over C2. And so then using this, our Q1 prime over our C1 is equal to our Q2 prime over our C2. And then using that, our total is Q1 prime plus Q2 prime. Then we can say that Q1 prime over C1. So Q2 prime is Q total minus Q1 prime. So Q total minus Q1 prime over C2. And now we can rearrange and say that our Q1 prime onto 1 plus, nope, yeah, 1 plus C2 over C1 is equal to our Q total, or our Q1 prime is equal to our Q total over our 1 plus C2 over C1. Did I do that right? Yeah, I think so, yeah, okay. Which is equal to our Q total times just giving common denominator here and flipping, which is our 10.8 times 10 to the minus 5 coulombs times our C1, which is 6 microfarads over 6 microfarads plus 18 microfarads. And so our Q1 prime comes out to be 2.7 times 10 to the minus 5 coulombs. And then our Q2 prime can be just figured out from the difference. Which is 8.1 times 10 to the minus 5 coulombs. And then now we can verify by saying that our voltage should be 2.7 times 10 to the minus 5 coulombs over 6 times 10 to the minus 6 farads. And it should equal our 8.1 times 10 to the minus 5 coulombs over our 18 times 10 to the minus 6 farads. And we can verify that indeed we get 4.5 volts in both cases. So that's as asserted. We asserted that the voltages should be the same, and they come out to be the same, so we didn't make any mistakes. So there's our potential differences across each capacitor. So now our energy stored is 1/2 times the capacitance times the voltage squared. So before they're disconnected, we have our equivalent capacitance. So our C12 is 4.5 microfarads. So our energy was 1/2 4.5 microfarads. Our voltage was 12 volts squared. If we do this out, it comes to 3.24 times 10 to the minus 14, times 10 to the minus 4 joules. And then after we reconnect them, we now have two separate capacitors in parallel. So it would just be C total is C1 plus C2, which is 24 microfarads. And so our energy is a half times 24 microfarads times the voltage we solved for, which is 4.5 volts squared, which comes out to be 2.43 times 10 to the minus 4 joules. Okay, so checking our solutions here. So up to the top here, so I don't know what was circled there. So our equivalent capacitance is 4.5 microfarads. So we got our total charge as 5.4 times 10 to the minus 5 coulombs, or 54 microcoulombs. Our total charge is then 10.8 microcoulombs, or 10.8 times 10 to the minus 5 coulombs. So continuing down here, so we get that our voltage difference is 4.5 volts, so that's good. Our energy stored before is 324 microjoules, or 3.24 times 10 to the minus 4. And then afterwards is 243, or 2.43 times 10 to the minus 4. So that looks good. Okay, we have three dipoles connected, or three dipole system in which they're side by side. They each have the same magnitude and the spacings are identical, and in which arrangement is the potential energy greater. So our potential energy for two charges is Q1, Q2 over R. A dipole system, though, is a dipole is a charge times a distance, or a displacement. So, and where we usually have two oppositely charged species at either end. So this is kind of our simple dipole. And so it's actually a vector quantity. Okay, so then the electric field due to two interacting dipoles, or the potential energy due to two interacting dipoles, is a little bit more complex, where we have our R vector goes, or our displacement or distance R goes between the two dipoles. And it's just mu1 dot mu2, and then some other factors that account for some other. Now, if our dipoles are side by side, then they are perpendicular to their R, and so then this term will go to 0. And so we just need to consider, and if they're perpendicular as well, then this term will just be 1 over 4 pi epsilon naught R cubed, mu1, mu2, cosine of theta, where theta is the angle between them. And recall that that if they're lined up, theta will be 0, so cos theta is 1, and if they're anti-aligned, then theta is 180, and then cos theta is minus 1. So then, so for A, we have an arrangement like this, where each of these r's is the same, and then that's 2r. So our potential energy between the first two would be minus mu1, mu2 over 4 pi E naught r. R13 would be mu1, mu2 over 4 pi epsilon naught times, so that would be r cubed, so 2r cubed. And and U23 would be minus mu1, mu2 over 4 pi epsilon naught r cubed. So our total would be, there's two of these negatives, and then this positive value. Now if we look at the B configuration, where again that we have RR and 2R, U12 would be mu1, mu2 over 4 pi epsilon naught r cubed, U13 and U23 would be similar to U12, and so then our total would be completely positive, and in fact would be pretty much the same except positive instead of negative for the first term. And so as this one's completely positive and A has a negative term, I would have to say that B is the greater energy. So B configuration is greater than the A configuration. So looking at our solution here, PE cos theta. Okay, so they computed it from the electric fields in each case, but that's okay. In the end, we get that that the second configuration is greater. So that looks good. Okay, so now we've got a football, and it's asked what minimum impulse must be imparted to a football of mass 0.405 kilograms to have a horizontal range of 39 meters. Okay, so we have to kick it such that it goes at some velocity and some angle to get out to 39 meters. And it asks what minimum impulse. So our impulse is delta P, which is F delta T. So our delta P is PF minus PI. Assuming it starts from rest, then that will be 0. So it's just our final momentum. So what final momentum must we give this football? And remember that momentum is mass times our velocity. Now in this case, I've called this VI up here, but I guess that's our VF in retrospect. So now we can figure out what velocity it needs to have to cover this 39 meters. So first of all, if we have our VF, this is the Y component and the X component, and there's our theta. So we have some VF cos theta is our VFX, and our VF sine theta is our VFY. Now, if we look in just the X direction, we have all the forces come out to be 0, so then our acceleration is 0. And so then our X, using our kinematic equations, plus V naught X T, and we don't need to worry about acceleration, and our X naught is going to be 0. So our V naught X T is just our XF, or our V naught X is just XF over T. Okay, so now we can look at our Y direction and see that there is acceleration. It's going to be just minus G. So we have YF is equal to Y naught plus V naught YT plus 1/2 AT squared. So that's going to be 0. And in fact, when it returns back to the Earth, that's going to be 0 as well. So our V naught Y is equal to minus 1/2 AT. So then our T is minus 2 V naught Y over A. And as A is minus G, then we can say that T is 2 V naught Y over G. And we know that that our V naught Y is our VF sine theta from above. So then this is 2 VF sine theta over G. And now we can use this time in our V naught X expression above. So our V naught X is our XF over T. So it's XF over 2 VF sine theta over G, which is XF G over 2 VF sine theta. Now our V naught X is VF cos theta, and so that equals XF G over 2 VF sine theta. We can now rearrange this to say that VF squared is equal to XF G over 2 sine theta cos theta. Now, this is a trig expression, so sine of 2 theta is equal to 2 sine theta cos theta. So then this is XF G over sine of 2 theta. And now we want to find our minimum impulse, so our minimum velocity that we need to impart to the football. So our distance is fixed at 39 meters. Our g is a constant. So the only thing we can really minimize is our sine 2 theta, or our 1 over sine 2 theta. So this will be a minimum when this is a maximum. All right, because if this gets any smaller, then this needs to get bigger. So sine 2 theta, but sine can only be between minus 1 and 1. So sine of 2 theta is a 1 at maximum. So then 2 theta equals 90 degrees. So theta equals 45 degrees. So if this equals 1, then our VF squared is equal to 39 meters times 9.8 meters per second squared. So our VF is 19.55 meters per second. Okay, so now our impulse, our minimum impulse is delta P, which is equal to just our PF as we said. And so it's our mass times our velocity, which is 0.405 kilograms times our 19.55 meters per second, which comes out to be 7.92 kilograms meters per second. Okay, so then it asks, so that's the first part. So there's our minimum impulse. And now, assuming that contact with the football is maintained as it moves 16 centimeters, estimate the time and average force. So our delta P is F delta T. But also, so we're given distance, so that always makes me think of potential energy. So delta U is minus F delta X. But recall that delta KE is minus delta U, so that just equals F delta X. Our delta KE is going to be just 1/2 m VF squared. And so then that equals our F delta X. And it's just that because our initial velocity is 0. So then our force is 1/2 m VF squared over delta X. So 1/2 0.405 kilograms times our velocity that we solved for, so 19.55 meters per second squared, all over our delta X, which is 0.16 meters. So that's 16 centimeters in meters. And so this comes out to be 483.725 newtons. So that's our average force. And then again, delta P is F delta T. So our delta T is our delta P over F. Our delta P was 7.92 kilograms meters per second. And our force that we just solved for was 483.725 newtons. And this comes out to be 0.0164 seconds. And so then there's our force and our time. All right, so checking through the solution here, the impulse is 7.92 Newton seconds or kilogram meters per second. We get a time of contact of 0.0164 seconds and a force of 484 newtons or 483.7. So that looks good. Okay. So here we've got a couple charges. So we've got X, XY, and now we're placing a 20 nanocoulomb charge at 2 meters and a at -3 meters in the y direction. We've got a -25 nanocoulomb charge, and it wants to know what is the direction of the electric field at the origin. So electric field is a vector quantity, so it's 1/4 pi epsilon naught. The charge over r squared times r hat, which we can write as 1/4 pi epsilon naught charge over r cubed times the r vector. So start off for the first charge, r10 is the distance to the origin minus the first distance. So 0 minus 2 meters x hat, which is then just -2 meters x hat. So there's our vector. Our r is just the magnitude, which is then just 2 meters. So then our E field is 1/4 pi epsilon naught times our charge, which is 20 times 10 to the -9 coulombs over our 2 meters cubed times our -2 meters x hat, which comes out to be -44.94 newtons per coulomb in the x hat direction. Now our R20 vector is again just R0 minus R2, which is 0 minus our -3 meters in the y hat direction, or just a positive 3 meters in the y hat direction. So our E field is 1/4 pi epsilon naught times our charge, which is -25 times 10 to the -9 coulombs over our 3 meters cubed times our 3 meters in the y hat direction. And that comes out to be -24.97 newtons per coulomb in the y hat direction. And so now if we look at this, x, y, so our force, or our electric field, sorry, is our total electric field is the sum of the two, which is -44.94 in the x hat and 24.97 in the y hat. So nothing really to add up there. And so we can get our angle, or at least we can get our angle in here as tan gamma, just going to call that gamma, is opposite over adjacent, so 24.97 over 44.94, which gives us an angle of 29.05 degrees. Now, we always measure it from the x-axis, so we need to get that whole angle. So the theta we're looking for is 180 plus gamma, so 180 plus 29.05, which comes out to be 209.05. And if we look at the answers we're given, D, 209 is the closest to this angle. Checking through the solution here. These are vector quantities. So EX is 44, EY is negative 25. So we need to add 180 to the angle, and we get 209. So that's the magnitude. Oh wait, what? How did you get that? Oh yeah, okay. So that's the magnitude. Okay, so that looks good. And I'm actually going to stop here now and say thank you all for watching. If you enjoyed this, please subscribe to the OneClass channel. If you want to leave questions, please follow please look below the video. This has been Jeff Kress for OneClass, and I hope to see